Supervised machine learning is often explained through a human metaphor, a teacher showing flashcards to a student until they begin categorizing objects on their own. In practice, the algorithm performs a mechanical operation. It takes a high-dimensional array of input data and maps it to a specific output label. We represent this setup with formal notation. The algorithm is provided with a training set of n examples. Each example consists of an input vector, denoted as xi, and its corresponding known output label, yi. The algorithm's objective is to discover a mathematical function that maps the input space, x, to the output space, y. Supervised learning executes a brute force search for an optimal mapping equation within a defined mathematical universe. An algorithm is mathematically restricted to choosing a solution from a predefined universe of possible functions. This coordinate plane plots a field of x and y data pairs. The candidate functions flashing across the screen represent the hypothesis space, G. Every line is a candidate function, G. The algorithm must select just one. This presents a mechanical problem. The algorithm requires a method to score these competing curves to determine which G is objectively the best fit. Selecting a function that fits the training points but ignores the underlying trend means the model will fail to produce accurate results when exposed to new, unseen data. We calculate the model's accuracy using a metric called the loss function. This measures the vertical distance between the model's predicted value and the actual true data point. To evaluate performance, the model calculates the expected loss across the entire training set. This total aggregate error is defined as empirical risk, or R empirical of G. Empirical risk minimization is an optimization strategy searching for the function that shrinks this error to zero. Pursuing zero error forces the model to account for deterministic noise. The resulting function becomes jagged and complex to intersect every outlier. We call this state overfitting. The algorithm has effectively memorized the specific noise of the training data rather than learning the rule. Achieving perfect accuracy on historical data indicates the model has lost its ability to generalize to future inputs. To prevent overfitting, engineers must constrain the algorithm, limiting its ability to choose overly complex functions from the hypothesis space. Structural risk minimization addresses this by adding a regularization penalty to the algorithm's scoring criteria. This equation defines the new objective. On the left is empirical risk, seeking accuracy. On the right, the C of G term represents complexity. As the function becomes more jagged, the complexity penalty increases. The cost of complexity eventually outweighs accuracy gains, raising the total cost, J of G. This penalty functions as a mathematical Occam's razor. When two functions yield similar error rates, the algorithm is forced to select the simpler one. Solving a supervised learning problem requires discovering the precise lambda value where the model is flexible enough to learn, but rigid enough to generalize. Simple 2D coordinates rarely reflect modern data reality. Input feature vectors often possess hundreds or thousands of dimensions. This leads to the curse of dimensionality. As dimensions increase, data points become increasingly sparse, leaving vast distances between examples. This sparsity causes variance to spike, as the learning algorithm struggles to connect these distant points without creating an overly complex function. In high-dimensional spaces, the penalty term CG provides the constraints necessary to keep the algorithm's prediction stable. Because different datasets possess different geometric properties, no single algorithm, such as a support vector machine or a neural network, is universally superior. Engineers must manually analyze the input space for nonlinearities, redundant information, and inconsistent data types. The engineer's role involves selecting a hypothesis space that fits the data's geometry and then tuning the penalty through cross-validation. The efficacy of supervised learning relies on the engineer's ability to mathematically balance empirical truth against structural simplicity.